All right, so auxiliary particle filters are cool, but this is also the hardest thing for me to teach. This entire term of everything I'm going to teach, like this is the topic that I always sweated on because there's a lot of math and it's difficult to explain, but I'll do my best to give you a good intuition for this. And you can go through the math on your own time. I'll go through it slowly, but I think the first time through, don't be too frustrated if you don't follow it all, especially at the end of the day, because it's not easy. It's not easy for me either. But there's a cool underlying idea, and I'll do my best to make sure that I convey what the idea and what the goal is clearly. And I think part of the reason I chose this particular extension to particle filters is that when we talked about the optimal importance density, and we ended up with 2 of them, and we're like, how did we end up with 2? And one of them was based on the fact that we were limiting ourselves to doing a recursion because we couldn't sample from part of the importance density. I'll get to this in a minute. But auxiliary particle filters are kind of a neat, clever way of overcoming that. There's some approximations, but aside from the limitations of those approximations, this is elegant, even though it's mathematically intense. So bear with me. I'll do my best to explain this clearly. This is just an overview of what we'll be going through. All right, here we go. Remember, there's two posterior probabilities that we keep in mind and that we work with. One is what I usually call the joint posterior, and the other one is the marginal posterior. So one is looking at the entire trajectory of the state from 0 to time in, given all the measurements up to the current time. And the other one is just looking at the state vector at the current time, given all the measurements from the beginning of the recording up to the current time. And one of the things we're doing with particle filters, or at least one way of understanding them, is that you can think of it as though we're modeling the posterior probability as a weighted sum of impulses, where the weights, of course, sum to 1, so that if you integrate this whole thing, it integrates to 1. So we've got this kind of very strange approximation of the joint posterior. But it's a very convenient representation for particle filters. Even though it's weird, it has some nice properties. It does converge to the true probability and expectation, as we've talked about before. It's one of the really nice things about it is we take this very complicated high-dimensional thing, and now we've reduced it to basically a set of what we call particles, the trajectories that we keep track of, and the weights associated with those particles. And so it's a very compact representation of a very complicated high-dimensional thing that normally you just couldn't represent very well. It's very general also. And as we know, the weights are the ratio of the posterior divided by the probability, or the PDF of the importance density, which we get to pick. I keep emphasizing this is a design choice. But one constraint that we have is it's got to be something that we can draw samples from. And that's why it came up in the first place, is that we couldn't draw samples directly from the joint posterior. If we could, then we wouldn't have any problems with weight degeneracy and life would be good. We wouldn't have to resample, everything would be more elegant, but we couldn't sample directly from this thing. But now, the question that comes up, though, I keep doing this to you, is I say you can't do something, and then I raise the question again, and I say, well, maybe we should take another look at that. Maybe we can, or maybe we can get close to that. So one of the things that I'm going to ask you to reconsider is there a way in which we might be able to design our importance densities such that we could actually possibly draw samples from the joint or get close to that?
I guess I was kind of wondering about that, because we can estimate the CDF from our estimate of the marginal posterior, and then do like uniform sampling to get draws from the CDF. I was wondering why we don't do that.
Single dimensional is easy, multi-dimensional is difficult.
Yeah, that's exactly right. In one dimension you can do that.
Yeah.
But in 10 dimensions, or even in 3 dimensions, you can't.
Is that because there's no consistent way to construct a multidimensional CDF such that you're guaranteed? Is it dimensionality
You
problem?
run into the
Okay.
curse of dimensionality. Yeah, that's right. That's right. It's a good question. Okay, so I want to revisit this question. Is there some way in which this might actually be set equal to something kind of like that? Is there a way in which we might be able to do something clever there? So this is review, just reminder, the whole class is driven essentially by Bayes' theorem. Working in this Bayesian framework, the thing that we're trying to track is random, and the way we often break that out is we start off with some kind of joint, and then we write this as a product of a conditional probability and a marginal probability, and we usually do that two different ways. So the way that we did this when we were talking about the state space tracking framework is we started off with this is our joint probability, and we wrote this as the posterior that we're actually interested in, this constant that doesn't depend on the state, the likelihood, and actually Bayes' rules applied again to break this out, but then we've got the what I've been calling the prior, and then we've got what the posterior was at the previous time step. So you can write this joint probability out those two different ways, and if you solve for the joint posterior that we're interested in, then we end up with a single elegant equation that looks really beautiful. And again, this thing down here you can think of as kind of a scaling constant to ensure that it integrates to 1. And so this whole thing is proportional to the likelihood times the prior times what the joint was at the previous time step. So we've seen that a number of times now. That's just a review. But it's an important review because we want to think about is there something that we can leverage here to get at our importance density. And another way in which we could factor out the joint posterior using Bayes' rule is instead to pull out the term x of n and make that kind of the term that goes into the marginal where it's conditioned and everything else. And then we end up with this. But when you break it out this way, now we've got the probability of the state from 0 to n minus 1 conditioned on y of 0 to n, not n minus 1. So when you factor it out this way, it's different than what we had before. And this is kind of a difficult thing to work with because we're looking at the probability of the state trajectory only up to time n minus 1, but now there's a future value of the measurement involved. And so the measurement is one step ahead of the last element of the state trajectory. And when we were looking at a recursive form of the importance density, again, this is something that I emphasize because it's something I struggled with when I was learning this material myself. I said, well, okay, we have this, and the books and tutorials often just factor it this way and don't emphasize the fact that that there was something happened here to the nth measurement. But it makes a big difference. And the answer was that we made this decision to condition this only on the measurements from 0 to n minus 1 so that this whole thing could be made recursive. It enables us to say, we advance our particles to a certain point in time, and now we can advance them from their current state to time n, just working with this part of the importance density, just the part that gets us from n minus 1 to n. Whereas we couldn't do that with this because this requires that the way your particles got there requires that they also take into account that nth measurement. So there was a choice we made there that enabled us to generate the particles recursively. And with auxiliary particle filters, we go back and we're re-examining whether that really was a good choice, because as soon as we did that, we ended up with a different importance density being optimal. When we tried to minimize the variance of the weights, we ended up with something that was completely different than the joint, which we knew was optimal to begin with. But it was because of that choice that we ended up there. So let's have another look at this. Suppose for a moment that we could actually somehow, and I'm using one of those words, so you got to be careful. Approximately, as soon as you hear the word approximately, you got to wonder whether there are any kind of convergent whether it will still converge the right thing or not, whether the optimality properties still hold. But imagine for a moment, maybe even drop the word approximately. Imagine for a moment that we could actually sample from this somehow. Or let's consider whether that's something we might be able to do. So let's say we can draw samples from that now. So if that were true, then we might actually be able to use the optimal importance density. Because we can factor it this way, and if we can somehow draw entire trajectories from 0 to n-1 here, then we've already solved for the optimal importance density of what this ought to be. But then it combines with this in such a way that we actually can make this equal to the full joint posterior if we want to. So is there a way in which we might actually somehow draw particles? And a lot of math is going to go into what is the way in which we might do that. And in order to do that, I want to emphasize this is seemingly a hard problem. This is something that, as a researcher, I wouldn't have thought about doing because just looking at this equation, it would have scared me away. It's hard enough to think about sampling from a posterior probability, but this thing is worse because this is actually doing a sort of a one-step ahead smoothing in a way, because this is talking about drawing an entire trajectory from a weird high-dimensional joint probability that takes into account not just the past and current measurements, but also one measurement from the future. And so I would have looked at this and said, no, I can't go anywhere from here. But there were some clever people that thought of a way out of that problem. And it starts by recognizing that we're already kind of close. We've already got something kind of close to what we need, because we've already got this approximation of the posterior, the entire joint posterior, that does take into account all the measurements up to time n-1. So that's kind of an asset that we have. The whole particle filter framework is the idea of representing the posterior as these weighted combination of impulses. And so that's something that we already have. That's something that we can use. So now this problem starts to look a little bit more manageable when we say we just got to get from here to figuring out how to take into account that new measurement, yn. Because we've already got this. Is there a way in which we can leverage that new measurement to get a probability that we can actually draw from? So this is where the math comes in. This is where it starts to get a little bit complicated. One thing that we do know is that one expression for the thing that we have, the thing that we're after. So here we've got I'm going to call this the smoothed posterior because it's using a measurement from the future. So it's analogous to the smoothing problem. So this smoothed posterior can be written as integrating out the most recent element of the state vector from the joint posterior. So that's one way in which we could represent that. And we already know, because of Bayes' theorem, we've been working with this in a lot of different ways. There's a lot of different ways we can write that. We've gone through this a lot of different times. So you should be comfortable by now with the idea that the joint posterior is proportional to the likelihood times the prior times what the posterior was at the previous time step. So we've got this whole thing, and we can put that into, or at least we can try to put that into this integral. So let's look at what happens when we do that. So our joint posterior is proportional to this. This is the smooth posterior that we're after, and it can be written as an integral where we're integrating out the most recent element of the state vector of our joint posterior. And so if we substitute this in, and again, it's only proportional to, so this is within a scaling factor, a constant scaling factor. But the smooth posterior is then proportional to substituting this in for this expression to this integral. And if you look at this carefully, you'll notice this last element of what we substituted in is not a function of the variable of integration. This is, we're integrating over the state at time in. The state at time in is not included in this function, and so we can pull that outside of the integral because it's effectively a constant as far as that integral is concerned. So we can write this as a product of the previous point joint posterior times this integral. And this integral is starting to look more manageable because you're already familiar with how to get this from the measurement model and how to get this from the process model. So we're starting to get closer to things we can handle, although, of course, we don't like integrals because they're difficult to do efficient computing with, especially when you've got a million particles like Andy likes to use. Should I stop giving you a hard time about that? So the approximation that we have of the posterior at time n-1 is, again, this weighted combination of impulses. And we know how to compute that because we've been computing that with particle filters. You all did that for homework 3, and you'll be doing that for homework 4 if you haven't been doing that already. And so if we substitute that into the expression that we now have for the smooth posterior, it's just this term right here. But one of the things that one of the properties of impulses, these Dirac impulses, that I hope you all remember, is that if you have an impulse, and I'll write this as a function of u just to make it clear, so u minus u naught times some function of u, this is equal to the impulse u minus u naught times the function evaluated at u naught. Right? I don't know if you all remember that property. Graphically, the idea is if you've got an impulse over here at u naught, and this is the u-axis, and you've got some weird function that is our f of u, because this product is 0 at all values of u except at u naught, if we had a constant function, sorry, I should have used a different color, but this is f of u naught, as long as it takes on the same value as f of u at the only place where that impulse occurs, then the product is the same. So that's the idea. It's a property you've seen of impulses used in many other classes. So, so the way that comes up here is that this impulse is of the state, but it's located only at where that particle trajectory is. And this was conditioned on x of n minus 1, and so we can take that element of this trajectory and make it just at where the particle is located, because it's an impulse because of this property here. And this is a bit much, this next step, but you know it's hard to fit all this math in a set of slides that I can project and you can see. So let's say that we now take whatever this integral evaluates to be. It's just an integral, and for this integral, you know, it's conditioned on something that we know. This is part of the particle. We know what the measurement is, y of n, because we measured it, and we're integrating out x of n. So this whole thing just becomes some kind of number. And we can lump that together with this weight and put those together and call those v, I'm going to call those v. So that whole thing becomes v n minus 1I times this impulse. And now we end up with a weighted sum of impulses that is a representation of what we're after, which is the smooth posterior. And it's in a form that's very helpful to us, it turns out. But there, you know, there's a bit of mental magic here, and I should probably take a step back and explain what on earth just happened. We started off with knowing what our posterior was at time n minus 1. And suddenly, using exactly the same particles, we ended up with a smooth posterior that was conditioned on y of 0 to n. So we snuck in that nth measurement in this integral, and the effect, after doing all this math, is that we end up with a representation where we have exactly the same particles we had before. We didn't have to regenerate them. It's the same particles, but now they have different weights. Let me pause, give you just a second to digest this and see if you guys have any questions so far. We're not done, but there was a lot that just happened.
So effectively, the smooth likelihood function, or the likelihood function given the next y's of n, is already embedded in the previous particle weights. So we're just taking advantage of that to change the particle weights given knowledge we already have about what the next measurement will be.
Yeah, that's a really good point. All the information from the previous measurements was already in our representation of the posterior at time n minus 1. And so we did leverage the fact that we're dealing with a Monte Carlo process, and so really we just needed to do an update to account for the new measurement we had. We didn't have to go through and change everything all over again. Yeah, you're right about that. That idea is correct.
So this integral will be evaluated once for each particle, right? And that becomes the new weight update for that particle.
That's correct. Although we're gonna need to think more about this integral. I think that's apparent by now because it's hard to do computation efficiently when you've got these integrals. You know, all the integrals we deal with are multidimensional, even if it looks like you've got one thing here, because this is a vector.
Right.
So this is a nasty multidimensional integral, and we're going to have to figure out how to deal with that. That's not solved yet. But assuming for the moment that we can get past that and come up with a way of evaluating that integral, now we've got a nice representation of this smoothed, the smooth posterior, and the critical. Well, I'll get to it in a minute. Let me go ahead. So. So this is taking, you know, the v of n minus 1. Here's the equation for the v of n minus 1. These are called the parent weights. So the parent weights are equal to our particle weights times this integral. And again, that integral is where that measurement comes into effect in that likelihood. So if we combine that with our earlier results, remember we were looking at an importance density where when we factor it as we did before, but now we wanted this to be y0 to n, and now we've got it. You know, this expression now could be these impulses with the weights, where the parent weights are given by those equations. So now we've got something that is like that. And this is an approximation because, of course, it's not perfect, but it's an estimate that converges in expectation of the right thing so far. So that's pretty good. That's pretty good. It's starting to look promising. But we're not done. We need to still figure out how this new thing is how the I don't have this quite right. We need to figure out how our importance density, our previous importance density is going to be related to, and this should be n minus 1. You can see that's what I end up with down here in the final equation. So relating it to the previous joint posterior. Make a note of that on the slides. So more math, although I was looking at this, I don't think this math is actually all that impressive or even really needed, because we know the joint posterior already is approximated as the weight of the particle times this, and we're essentially replacing that weight with now the parent weight. So, you know, I think I could have done that in 1 or 2 steps, but the math here is valid as well. We say we're going to choose our importance density, so it's now given by these parent weights times the same particle trajectories. We can, of course, multiply and divide by the same number. Because these are impulses of the trajectory from j minus I can change the index from I to j, pull that outside the sum. This is just what the previous joint was, and so we end up with this ratio times what the joint was at the previous time step. But there's not really that much intuition here. But things do get a little simpler if I attempt to put it all together. We know that our weights are always proportional to the ratio of the joint posterior divided by our importance density, whatever that happens to be. We know that our joint factors is the likelihood times the prior times the previous joint, the joint at the previous time step. And now we've chosen our importance density, so it factors as the thing that advances, whatever the probability is that advances the state from the previous time step to the current time, multiplied by this new probability that we're going to use, that we know from the previous slide can be expressed as a ratio of the new parent weight divided by the old particle weight times our estimate of the previous joint. And so when we look at the weight update equation and we take the ratio of these two, I substitute, the expression for the joint from this line, divided by the importance density given by this line, then you end up with this, this somewhat complicated expression. Because this is in the denominator, this is V over W, but because it's in the denominator, those flip, and so we end up with the weight being on the top. And if you look at this carefully, if we can assume that our approximation of the previous joint probability is a good one, and it's essentially equal to what the previous probability was, if you can accept that that approximation is a good one, then those cancel, sort of. And we end up with a simpler expression for our weight update equation, which is given by this final equation here. So we have the very familiar likelihood, the prior, our importance density for advancing from time n-1 to n, and then we've got the ratio of the particle weight at the previous time step divided by the parent weight. And that's how we can update those weights. I'll get to a simple algorithm. All this math, of course, ends up being really, really simple at the end of the day. A common choice that we've made in the past is to use the importance density for going from time n-1 to n of just setting that equal to the prior, because then you're just feeding data through the process model, and that's very easy for us. And so you get a similar cancellation that you get to the traditional particle filter, where if that's your choice, then you get a cancellation of the prior here and the prior there. They cancel, and so you end up with simply the ratio of these weights times the likelihood. But if you do that, we know this is not the optimal importance density, so you just lost the idea that this is in any sense going to be asymptotically optimal or approximately optimal.
Hopefully optimal.
Did you say hopefully?
Yeah.
Nice. But this is a lot better. We still have an outstanding problem that I haven't quite addressed yet. And there's something that I didn't make clear enough before. One of the things we have to do, I said, this is really hard, is drawing particles from the smooth posterior. But now we've got a representation of the smooth posterior where it's these impulses with weights. And we actually already know how to draw samples from that kind of distribution because we did exactly that when we were doing resampling. When we resampled, we were also redrawing from the posterior PDF and resampling. And so we can use exactly the same code, do exactly the same here, it's just we've got a different set of weights. So suddenly that very difficult problem of drawing samples from, and I should have had that equation on the slide, but drawing samples from this Q of x of 0 to n-1 given y of 0 to n. The problem of drawing from that generally is really hard. It's harder than the problem we started off with, of drawing from the posterior. But if this really is approximately equal to some weighted combination of, I should have made that different. I don't see where the undo is. Oh, come on. Is that not an eraser? I guess that's not an eraser. Oh man, fail. Sorry, but I think you get the idea. It's a weighted sum of impulses in high dimension. We know how to draw samples from that with resampling. So suddenly this is in a form that we can actually use for our purpose. And that's really elegant and cool. We can suddenly draw that, draw samples from that. So that's really neat. We're using the measurement now to help us draw samples from the past trajectories. We're not resampling, we're doing something called pre-sampling. And this dependence on y-event is called adaptation by the folks that cooked this up. So that's pre-sampling. I should have just advanced the slide. What I needed was right here. And the really cool thing, again, is that we're actually using that nth measurement. So we've got these weights that we need to calculate, and the weights are equal to the particle weights times this integral of the likelihood times the prior. We know what both of those are, but doing computation with integrals is hard. And so this is where things get a little bit ugly. We can pre-sample parent trajectories. We can look back and pick kind of the best parents, taking into account this measurement. But the way that they get around the idea of evaluating this integral is they say, let's assume that that this prior probability is an impulse, because integrating impulses is easy. We can compute with that. Let's make that an impulse, and we'll make it an impulse where it's x of n minus f of x of n minus 1. And if you think really carefully about that, we're approximating a probability as an impulse. A probability has unit area, an impulse has unit area, so they share that property. They're both non-negative. So, it's kind of sounding somewhat reasonable. But when a probability is an impulse, when a PDF is an impulse, it basically means you know where it is. There's no uncertainty. It's equivalent to having no process noise. It's equivalent to having a deterministic process model, which we don't have. But that is the solution that they came up with of being able to compute with this integral. And that's where the bit of kind of inelegant ugliness is in this approach, in my opinion, is in that approximation there. The approximating, for me personally, approximating a posterior as a weighted sum of impulses doesn't bother me so much, because in the limit there is a convergence property around that. But there's no convergence property here. This is just kind of a coarse approximation that enables them to evaluate that integral. So again, it makes sense if your process model is that x of n plus 1 is just some function of what your state is at time x of n. So it would have worked very well. And I think it was Ethan's example last time, where you had really good deterministic dynamics and a lousy sensor. So in that example, this arguably would have worked very well. In cases where you've got a lot of uncertainty and you're relying much more heavily on your measurements, this isn't going to work so well. So in terms of high-level guidance, that's about as much as I can offer you as to whether to make a choice between using an auxiliary particle filter or the basic resampling particle filter that I taught you first. So, but if you can accept this approximation of that probability, then suddenly this integral again compresses to something that's very simple, and it's simply a matter of evaluating the likelihood, where instead of conditioning on the particle at time I, you're basically taking what the particle is at time n minus 1 and projecting it forward with your process model. And in practice, instead of using the particle at time I, there's lots of other things that you could substitute in there. You could take the mean across your particles, or a mode, or a median, or a draw. I mean, there's all sorts of things you could do and various ways you could justify it. But in its simplest form, you would simply use whatever the particle is at that time and advance it forward that way. So this is the second approximation, and in my view, it's kind of the biggest weakness of this approach, is the idea that it's modeling the process model, so it's deterministic, when we know dang well that it isn't, in most cases. But it does simplify the weight update equation, and suddenly you can do computation with it. So we picked, there's a little bit more that you can do to simplify things. If we're using the prior as our importance density for moving one step ahead, then we had this equation for the weight update. And now we've got a simpler equation for what the parent weights are, where it's actually related to what the weight was at time n minus 1. So we end up with something that's kind of clever that happens, something that's actually very helpful to us. In that when we substitute this in, because that weight is there twice, we end up with a cancellation. And that makes all the difference in the world, because you might remember before, the reason we had weight degeneracy is because the weight at time n was a product of the weight at time n minus 1 times something else. And there's a lot of different ways that something else could be 0. And if it's 0, then as soon as you drive this thing to 0, it can never recover. There's nothing really to amplify it. That's why all the weights head towards zero, and we have the weight degeneracy, and you end up with just one weight dominating. But with auxiliary particle filter, that doesn't happen. Because of this cancellation, we end up with a weight at time n being a ratio of two things that doesn't degenerate. And so with these auxiliary particle filters, that problem is gone. The pre-sampling essentially replaces the resampling, and you no longer have to resample. So that's kind of a nice property of these. So again, taking a step back, auxiliary particle filters are just one of more than several. There's a lot of different general alternatives to the sequential importance sampling algorithm with resampling. This one is cool because it uses the observations to pre-select trajectories. Rather than moving the particles sort of blithely ahead, sort of blindly, you're just following the process model, and then their weights go to zero, and eventually it gets so bad that we have to hit the resample switch, and hit the reset switch and resample everything. This is different because it's using this measurement to pre-sample the trajectories. It's kind of looking back in time and saying, which of the possible parents do I even want to consider moving forward? So it's pre-selecting that rather than moving things forward until it gets bad enough that you have to resample. So it's really good. The only big weakness in my view, again, is the way that it handles this integral by approximating that as an impulse, which is analogous to assuming no process noise. So the process noise is large. This may perform worse than the simple algorithm, but if you've got something like what Ethan had, then it may perform beautifully.
It seems like there will be a lot of applications where we do not have process noise, or at least it's very smaller than much of the measurement noise.
Yeah, so this is a good choice in those applications, I would say.
Yeah. Another way of thinking here was that why degeneration occurs is because we have a bunch of particles in the space and we have some process noise. We don't know how the trajectories will evolve with time, and we go in all possible directions. So, and because the total space is much wider than plausible space, most of them will end up in unprobable locations, right? In this case, there is no process noise. We know exactly how particles should evolve, and so they don't just disappear into places they shouldn't go.
Well, that's sort of true. There's still, it's not quite right. I was with you until the very end. And the problem is that those, in some respects, those particles should be scattering out. I mean, our process model tells us that there is variability. I mean, you could argue, well, wait a minute, isn't this assumption that you've got a deterministic model for this integral?
Because of measurement noise, it will feed in.
Yeah, I mean, you went the opposite way. Before, we weren't taking account of the measurement was the problem. That's why they ended up in improbable places, and we had to resample. But now we're kind of doing the opposite, and we're really limiting the process model and not letting it scatter the particles out arguably as well as it should. But in resampling or pre-sampling, we are taking account of the measurement. So we're not waiting until things get super bad before we take account of this measurement. We don't have to resample. So, one of the things that maybe makes you nervous about resampling is if you set it at 10%, your threshold at 10% of the maximum number of affected particles. That means some of the time, 90% of your particles aren't doing anything for you. You're going along for a while where there are times where only 10% of your particles have significant weights, and you're burning a lot of computer cycles and something that isn't helpful. This doesn't have that problem, which is nice. The weights are not degenerating. It's not as though you have to set some kind of resampling threshold. So that is an advantage. But this fact that you've got a deterministic model is a little bit worrisome. And Amit, I said the wrong thing. I'm sorry, I screwed up in our conversation, because one of the things that I had said before is we still get to pick how we advance the particles forward in time. And so when we're looking at the part of the importance density that's conditioned on as much of the past as we want, I read it just as x of n minus 1, but it could have been 0, 2, n minus 1, and all the past measurements up to including the current measurement. One of the things I said is, well, let's set this to p of x of n given x of n minus 1 to the prior probability. And if you're doing this, we are actually moving our particles forward where they are able to scatter with the process noise. The problem is when we're calculating the parent weights. That's where we're using this approximation. It's not in advancing the particles forward. So they are still able to scatter out. But then when they scatter out, we catch them right away if they're scattered out in unlikely ways by taking account of that measurement. And so the pre-sampling is a little bit like resampling at every time step.
I was wondering about that. And in practice, how does do you just pre-sample once per particle? I guess I didn't get that part. What exactly the pre-sampling looks like in implementation.
So assuming that you're working with a constant number of particles, you don't have to, but if you're not going to, you should be able to justify why you're not. So assuming you're working with a constant number of particles, when you're figuring out what your particles are going to be at time n, for every one of those, you're going to pick a parent. And you can pick a parent based on this pre-sampling.
Identical to resampling, with slightly different non-uniform weights.
I would agree with that, except it's at a different point in the algorithm, and the weights are not slightly different. they're more than slightly different, I would argue.
So you're changing how your weights are updating to take into account that current measurement in a way that you weren't doing it before.
Yeah,
It's like, it's kind of like, if you think about it, it's like we're not really changing what our Q is, but the idea is we're basically only picking particles from regions using the current measurement, because at the point where we have to pick new particles, we have the information of Y events, we might as well use Y events.
That's right. And
with resampling, you get new particles, they're at new locations, but this is the same ones, they're just weighted differently.
well, maybe a good way of explaining the difference between the two, at the end of the day, is with the sequential importance sampling approach. We move our particles forward based on the, if we're using the prior, then based on the process model. So you say, okay, we know what our particle is at time n-1, stick it through the process model, that's going to tell me what it is at time n. In contrast with this, for the particle, for the ith particle, we first pick its parent. We don't simply advance it forward, but we say, which parent are we going to work with? So we find a parent trajectory, and then we go forward from that parent trajectory.
See, but that's what makes it sound exactly like resampling. Because if you resample at the first part of your loop, right? So if you code your particle filter such that you resample, then you do your process update, and then you do the weight update. Perfectly reasonable way to do it, right? Except most of the time you wouldn't need to resample everything. But this, you are moving around where those particles are before you update them, before you sample from your importance density.
I'm not sure it's reasonable to do the sequential importance sampling the way you described, where you're doing it before you advance them forward. You're resampling before you do that. But it would be similar. What you described would certainly be similar. But it would make me nervous. It wasn't what I taught, and I'd have to think about that to make sure that it's okay.
We just resample at the end, right?
We do.
But the end of one loop is the exact same as
It's the beginning of the next loop. I understand the reasoning. Yeah, it's a great question. I just don't know the answer off the cuff.
So, and you said that this was better for systems like mine where you have good prior knowledge?
We have little process noise, correct?
Little process noise. So, but do you run into problems then if you have, you have these, you're trying to include the measurement, which you know is more noise or is kind of worse than your process model, and then you're trying to make selections based on that? I get why you'd want to include your measurement, but if you know that your process model is quite good, would you want to depend less on the measurement then?
If you know, that's a good question. This kind of will do it already, because if this likelihood-like equation is very broad because you've got a lot of measurement noise, then then it's not going to change a lot across the particles, and your weights will be more or less uniform, I think. I think it still works even in that case.
Is it fair to say that if you're working on a model where there is almost no process noise, then auxiliary particle filter will have better performance than?
It's a very general statement, and I'm reluctant to make broad, sweeping generalizations like that. But using the word generally, I would say generally that's true, or at least my understanding is that's true. Again, I don't claim to be a deep expert in particle filters, but based on my understanding, I think that's true. I think that's right. So here's the algorithm. I mean, at the end of the day, after all this math, it does end up being pretty simple. And maybe it's simpler than I make it out to be. Maybe Walt's right, and I should say, well, this is really not different from just changing the order in which you do things in a loop. But I think it is different. But in any case, so we go through. The first thing we do is for all the particles, we figure out what the parent weights are. The parent weights are simply the particle weights now times this thing, which is our approximation of that integral. So you get the parent weights. We normalize them because these are unnormalized. We do that kind of resampling-like step, but in this case, again, we're picking the parent trajectories. And as soon as we've got all the parents selected, then we can go through and go forward from each of the selected parents to figuring out then what the sort of child is going to be of that parent for the state of that particle at time n. And then we calculate the weights, the unnormalized weights with this equation, and then normalize, and you've got your representation of the posterior. So that's it. I mean, it ends up being a very simple algorithm, really not that hard, much harder to code in than what we had before.
Sorry, what's JI? Like X, draw Xn from
It should just be xi, 7 minus 1, I think.
just I, right?
Well,
Yeah.
I don't think so. So the idea is that when you're doing the sampling, pre-sampling with these weights,
What JI,
that
which-
you're getting a different set of parents than what we had before. So if I had I here, then that would suggest that you're just going forward like we did with the traditional particle filter, where this is going forward from what it was. But the J sub I, the idea is that this is the parent, the new parent of the ith particle. So maybe what I probably should have done here is made this a J and made that a J. That probably would have been better.
So one more question. That Q x of n given x j I n and minus 1 y n, sampling from that doesn't seem straightforward.
Well, we've talked about this before. If you really want to maintain optimality, then you would use the optimal importance density that we talked about before.
Right.
If you don't care about that, then you would
Oh, that's what we did.
then you can make that whatever you want. You can choose a prior if you want to. I mean, you've still got latitude to make that what you want.
Right, but that's the optimal importance density we were talking about then from the other one.
It's an importance density that you get to pick.
Right.
Yeah. And I still argue choosing the prior is not a bad choice for that density.
Okay. Yeah, if you're using the prior, okay. Yeah. If you're using the prior, then this looks a lot like resampling every loop. I mean, it's probably a little different. It looks pretty similar at the same time.
Yeah, it's different but similar.
It's different because with resampling, you're using the actual weight of the particle, but here you're coming up with this pseudo weight v, where you're just propagating the previous state forward.
Yeah,
and
that's
it
right.
integrates the likelihood.
Before
That's
the
the goal.
the only place where yn was accounted for before was in the weight update. It's in the weights, and we'd drive them to zero, and like, oh, this one's no good. I'm gonna throw it out in the resampling. Whereas in this case, the pre-sampling is taking account of that measurement. So that's a difference.
Yeah.
That's a difference. Let's take a 5-minute break. I'll take any more questions you guys have. We'll look at an example, and then we'll be done. Right, so, any questions?
Now we figured it all out.
Awesome, awesome. Easy, huh? Well, let's see an example. So once again, the application that you're familiar with, I haven't, I didn't want to mix up because you're familiar with this process model and you know what the posterior looks like. So design decisions, for the importance density, you know, I went easy. I chose the prior. I didn't get fancy and use the optimal importance density. Even though we lose some of the optimality that we spent so much time developing, this whole idea was based on the idea of maybe we can sample from something closer to the optimal importance density. So it's weird to go through all that work for the one part and then just kind of throw that away when we get to this other part. For the number of particles, you know, there's the usual trade-off between performance and computation, and as much as you have patience for or whatever your budget is. I decided to push the limits in this case before I wanted to sell you on particle filters, and so I used 500, which was enough to show that it worked with something that's very fast on a modern computer. But in this case, with these auxiliary particle filters, I wanted to push the limits a little bit. And it is also true that you're doing that pre-sampling at every time step, so it would only be a fair comparison if you were doing resampling at every time step instead of setting a threshold based on something like the number of effective particles. But I'm not trying to do a apples to apples comparison. I just want to give you a sense of how this works. But do keep in mind when you look at the images, you're like, that looks worse than what I saw before. Well, it's with 1/5 as many particles, so it's intentionally going to be a little bit coarser than the earlier things that we've seen. And I'm just going to try to estimate the mean in this case, only because it's easy. I'm not giving you a good rationale. We already know it's multimodal. If this was a real tracking application, I would probably use the median. So we know what this looks like, and again, only 100 particles. And this is going to look a little different than what we had before. This is where all the particles go, but I can't really connect them any longer because I'm pre-sampling at every step. And so it makes less sense to think about a trajectory going forward because it's not going forward. It's like it goes forward one time step and then it may or may not be selected by the subsequent particle. You know, it may or may not be selected as a parent. So it's more trouble to think about what would be legitimate for connecting all the dots. So this is a little bit different visualization, but you know, again, the true state is shown in red, and you can see where all the particles landed. And you can see that there was at least one point where it was ambiguous as to whether the car was going backwards or forwards around the track for a little while. This is really cool. This is the same measures of weights we had before, where you remember they would all kind of head towards zero, pretty much exponentially, and then you could get resampling and they'd all go back to being the same, and then they would all head for zero again. It doesn't happen in this case because of that pre-sampling and the reasons I said before. The weights all stay small, which is good because no single particle dominates like what we saw before. So, you know, it's working, so to speak.
There you go.
So
Set
it-
up where you looked up.
But it is on the previous slide, so now the question you asked is going to be heard after I answer it. That's okay.
Ask it again. So it seems like right after 20 and right around 40, you kind of have areas where the variance in the weights go up, and then also what's the last one? Is the
Yeah, over here as well.
oh, it's just not on a log scale. The weights. You have some that are more selected. It seems like that's kind of in the areas where you have the multimodal and kind of splits.
Yeah. We can kind of see this gets a little bit thicker too. So you can see there are a lot more weights that are smaller in those regions where the variance is higher. I don't know if that corresponds to those splits or not. I just don't know. When we did the math before, we saw that the weights, if I'm doing this from memory now because I don't know how to go backwards, but I'm doing this wrong. The weight of the ith particle at time n, I believe, was equal to the likelihood of the ith particle divided by p of y of n given if we were to advance the particle's parent forward in time, it's pi minus 1, so it looked like this. So the variance will be high, some of the weights will be small relative to others when this ratio differs for some of the particles. And it seems to me that's going to occur when the deterministic process model that this represents is far away from this. So I suppose that's going to occur when we advance the particles forward in time and they scatter and they end up being far away from where they would be if we didn't have any process noise. I think that's when you're going to have high variance. But I'm thinking that through out loud as we go. That's not something I just knew the answer to, but I think that's probably right.
We're getting that multimodal actually because of the measurement model.
Yeah.
Yes.
Because it's
Well, it would kind of make sense too in this case, right, that the likelihood does get more spread out when you have the bimodal kind of points in time.
That's a really good point.
So in this case, I mean, it really comes down to that ratio getting different for certain particles, which causes that variance to go up. But in this specific case, it tends to coincide with points.
Yeah.
It is bimodal.
Yeah, that's right. That's perfect.
Do you get those spreads then at the times when there's high separation of the modes?
Yeah. You can see that where the, oh, hold it. I'm sorry, ask that again.
Do you see that higher variance or separation there in the weights at the times when there's a higher degree of separation between the modes? So like around time step 40 or time step 20?
Random recording.
No, I think blue's the one you want to do, because I think
Oh,
maybe by
okay.
scroll to the end it means of the audio, which is a really confusing word, but
Yeah.
I
Well,
think that might,
the end of the audio for that particular slide.
is it? For sure.
Yeah, yeah. Because I know
More
that
software
this
design.
program, they've got the wrong model in associating the audio specifically with slides, but that's how it was set up a long time ago. Anyways, here's the posterior, and again, it looks rougher because this is based on 100 particles instead of 500, so that's why it looks coarser than what you've seen before. And I'm going to advance forward. I'm not going to go backwards. I'm just going to advance forward to what the true is, calculated from the numerical technique that we started the course off with. So just visually watch to see what changes. Of course, you'll see the yellow will turn to pink, and you'll see where the boundaries are for the 95% confidence interval. And I'll add the mean as well. So this is the estimate, and here we go. I think I'm going to try that again. So inserted an extra slide, and it broke my whole drum roll moment. Anyways, this is what the optimal looks like. You can see there are times where the particle mean is far away from the true mean, like in here, and that the estimated posterior was overestimating how heavy, how much area should have been in that mode. But that's really just because I didn't use very many particles. That's primarily what caused that. So this is actually pretty dang good with just 100 particles. Here's a side-by-side comparison. And, you know, as usual, it looks pretty good overall. Again, you can see that this part is overweighted, but, you know, bottom line, it's doing a pretty dang good job with just 100 particles. So that's auxiliary particle filters. And just as a quick summary, unlike the systematic resampling, these are picking the best parents with this pre-sampling idea. It approximates an optimal sampling strategy. It approximates something that we didn't think we could do, but it does require pre-sampling at every time step. So arguably it uses a lot more computation than if you're setting just a threshold and resampling. It's more analogous to resampling at every time step. And again, the thing you got to be careful with is that approximation of the integral and how much process noise you have. If it's a good approximation, then of your process model, if you don't have a lot of process noise, then this may work quite a bit better. If you do, then you might be better with the simple SIS algorithm with resampling. And that's it. That's auxiliary particle filters. So So we'll stop there today, and on Tuesday, we'll talk about the Viterbi algorithm that you may have heard of. That's used a lot in communications, and we'll look at how that might be used in a particle filtering context. So it'll be good. And well, actually, we probably won't, because we'll probably spend the whole time with the homework presentation, so maybe we'll get to that on Thursday. But that's our next topic. You guys should have everything you need to get thinking about your projects, and pretty soon I'll ask you to do your project proposals. So start thinking about them.
I was curious about what qualifies as a reasonable project.
It was on the website.
Because I couldn't find, it is on the website, I looked at the syllabus and everything, and I couldn't find
It should be on the website.
It's not very
I was hoping he was
Do you
right.
mean the D2L website, or is there another
No,
website?
just D2L. Detail is the only website.
Okay, well, I
so
might
it's-
just be really bad at interneting.
No, it should be there. That doesn't mean it actually is there. I'll say some more about that on Tuesday. I'll take a look at it and make sure what's there is up to date.